Well, good afternoon, everybody. Thank you for joining today. Um, it's a privilege to interact with my colleagues from within and outside the university. Now, let me see if I can find my presentation. Okay, here we go. And I'll put it into slideshow mode. Hopefully everybody can see that. All right. Well, again, thanks for joining. I'm going to spend the next 40 minutes or so talking to you about hydrogen and what looks to be a potential new way to make it a more sustainable product. As we all know, hydrogen is a very important molecule in the energy and petrochemical space, and some believe that it's the energy of the future. That will remain a debate for the foreseeable future. Now, this work is done with my graduate student, Elmer Ledesma, who is on the call today. We will have a Q&A at the end of the talk. So let me proceed. Now, as a background, as we all know, there are endothermic and exothermic reactions. A large host of industrially important reactions require significant amount of heat to bring the reaction up to temperature and to overcome equilibrium limitations. So I'm denoting that by an A plus B kind of reaction. Now, the way industry conventionally provides the heat or energy to supply to enable the preheating and then also overcoming the heat of reaction is through combustion. And I'm denoting that here by an oxidation reaction with a much negative delta H compared to a potentially very large delta H for the desired reaction. Now, I'm going to spend the entire talk talking about steam methane reforming, or SMR for short. That's a very important endothermic reaction in industry. It's the main route to hydrogen. That has a delta H of 206 kJ per mole of methane reacted, compared to combustion, which, if one considers the same reactant oxidized to generate the heat, that generates a exothermic reaction heat of 890 kilojoules per mole. But it also generates carbon dioxide, another very important molecule. Now, SMR chemistry
Hey,
is
Mike,
shown
your
here.
presentation
Main
is not
reaction.
in the presentation mode.
Oh,
Display
sorry.
settings.
Okay, right. Okay, thank you.
So do the swap. Yeah.
Okay, thank you. So methane steam reforming main reaction is shown here, generating 3 moles of hydrogen per mole of methane reacted. It's endothermic and more favorable at high temperature, obviously. Now, a side reaction is the infamous water gas shift reaction. It converts CO basically to CO2 and is thought to approach equilibrium at high temperature, but it's a mildly exothermic reaction. Now, industrially, these reactions are carried out in tubular packed or catalyst packed tubes, many of them that are put into a combustion box where the chemistry is carried out. Temperatures as high as really 1500 degrees centigrade are obtained in this hot box where a fuel is burned generating carbon dioxide. And that's the way it's been done for many decades. Now, hydrogen is a growing demand product. It's forecast really to be approaching 200 or 300 metric tons per year by the early 2030s. consumed by many industries. So strong demand, and this demand is met in principle by steam methane reforming, producing on the order of 95% of the hydrogen worldwide. But that's done in an unsustainable way from a CO2 standpoint. This is a huge carbon footprint process. Nominally 10 kilograms of CO2 are produced per kilogram of hydrogen generated. And this poses a real challenge. So how can we reduce that number down to a manageable number to make hydrogen more sustainable? And that's where decarbonization comes in. So the Energy Transition Institute, one of the main topics of interest is decarbonization, and in particular, electrification. Now, the argument is that if one can provide heating through electrification and the source of the electrons are renewable electrons, then we potentially can take down this low-hanging fruit and make SMR more sustainable. Now, my colleague, Professor Vimuri Balakataya, published a paper with Ram Ratnakar from Shell a few years ago in AICHE Journal and proposed a new mode of carrying out endothermic reactions. Their particular focus was ethane steam cracking, but SMR would certainly be in the same family of reactions. Their argument is connecting modules of reactors to electricity sources such as wind and solar, which obviously are renewable sources generating minimal CO2. Those electrons are then used to ohmically heat substrates wherein the catalyst is either deposited or in the same locale as the heaters. So in principle, the idea is in principle to replace combustion as the energy source with ohmic heating from renewable sources going forward. Now, this is an active area of research. Dow and Shell are teaming up, as are BASF and SABIC with Linde. And these are European projects where electrification is being used to do steam cracking of ethane to ethylene, the main route to commodity chemical ethylene. That also being a strongly endothermic reaction, the thinking there is to make that process similar to SMR more sustainable. The approach that these companies are taking is basically to use metallic tubes that are ohmically heated using resistive metals packed with catalyst in close proximity to the hot wall, as opposed to bringing the heat in through a furnace box. So these are ongoing and really exciting projects. Now, the objective of our research, and this over the past few years was supported by Shell, is to investigate a Joule-heated coated catalyst concept for steam methane reforming. And what I'm going to do is walk you through some experiments that Elmer carried out and what our ideas are about what we're observing, which I think you'll find pretty intriguing, like we did when we went into this project. Now, how complicated can it be? Now, this is not to be too facetious, but it's just to emphasize a point. We all know that ohmic heating we do in our everyday lives. This is a toaster. You pass current through a resistive metal. It glows and gets very hot due to the friction imposed by the flowing electrons through the metal lattice. Joule heating is well known. Now, our idea is, well, taking a cue from these wires shown here in the toaster, what if we coat these wires with catalyst, SMR catalyst namely, and carry out or try to carry out steam methane reforming on an electrically heated and coated wire? So that's the idea. Okay, so I'm going to walk you through our experiments. We work from the ground up. We prepare catalyst and test the catalyst in a lab scale reactor, and then make observations and learn from these measurements at a fundamental level, but more importantly, come up with some ideas on how this might be scaled up if it works. Now, for those of you interested, we have a paper published in 2024 that gives some of our earlier results from this project. Today, I'm going to show some of those and some recent measurements that Elmer has made in the lab. Now, we start with a coil. This is a iron, chromium, aluminum metal, otherwise known as canthal. It's a common material that has the right kind of conductivity range wherein one applies a voltage across the wire and it heats up to a temperature of interest. This is going to be basically the reactor in the experiments we're doing, about 0.5 millimeter in diameter. This particular wire is about 45 centimeters long with 11 turns. For those electrically engineering interested folks in the audience, this is a solenoid, basically. One can produce a magnetic field by putting current through this coiled wire. I'll get back to that a little bit later. Now, the experimental setup is straightforward. First, we make the catalyst. The catalyst will be nickel-based on either zirconia support or alumina. The choice of the support, as I'll show today, is critical. Now, we do this coating in Professor Praveen Bellini's lab with his student Meghana, producing a coated FeCrAl, FeCrAl wire with a very thin layer of nickel zirconia. Now, the wash coat thickness, depending upon the gravimetric loading, the mass per area, is nominally 10 to 20 microns thick, not unlike the wash coat that we would see in a catalytic converter in our car. So we take that wire and then do some characterization, bring the wire into a reactor and apply a voltage across the wire with the purpose of heating up the wire and carrying out the chemistry. This is a layout of the straightforward reactor system that Elmer has constructed. We basically carry out SMR in what I'll call a single wire reactor using not somewhat diluted methane steam reforming feed of nominally 3 to 4 steam to methane ratio. We do some preheating, and then the bulk of the heating is done by the ohmic process, the Joule heated process. This is a picture of the coil spanning the cross-section of the tube. This is not a well-designed reactor. When you look at it immediately, you can see that there are potential regions for bypassing. Just envision that the ultimate reactor would be a staggered line of these coils down the length of the tube. The experiments we carried out have been so far with a single coil. So we apply a DC voltage in the range of 13 to 16 volts. That produces a power for the given resistance of the FeCrAl of between 50 and 90 watts. We then collect the effluent and characterize the unreacted methane, the produced CO and CO2. Now, this is an infrared camera measurement of a straight wire in which we've applied nominally a few volts across the length of this shorter wire, showing the temperature exceeding 450 centigrade. On the right is the measured temperature, which is a linear function of the current with the standard expression for I squared, V squared over R. So an energy balance for the non-reaction wire would include radiative losses, convective removal of heat from the wire, balanced by the ohmic heating. One can solve this equation for temperature and get a very good agreement between the measured average wire temperature and what simple theory predicts. Now, the approach we take is to tune the current, or really the applied voltage, to the desired range to effect reaction. So let me show you some results. Now, this is literally one of the first experiments that Elmer ran. Now, this is for a 10 weight% nickel on zirconia support that's coated on a FeCrAl wire that's then subjected to a range of imposed power between 50 and nominally 90 watts. Along with the coated wire is the uncoated wire in the red squares. Now, the green line for this particular set of conditions is the predicted equilibrium conversion. Now, there are some notable attributes of these data. First of all, as we would expect, the conversion goes to a high value at sufficiently high temperature. The temperature measured or predicted by that energy balance shows that upwards of 800 degrees centigrade, pushing 900, in that range, the conversion of methane approaches 90%. Now, that is not an unexpected result. We expect an endothermic reaction whose rate increases and whose equilibrium becomes more favorable to have a conversion approaching, hopefully, completion. And with this 4-to-1 steam to methane ratio, the equilibrium is favorable. Now, you can see, obviously, the catalyst has an important effect. Without the catalyst, the wire is basically inactive. Interestingly, we observed this sudden discontinuity in the conversion versus the imposed power or temperature that was kind of an unexpected result. We went into the experiment thinking we would get a kind of nice, smooth sigmoidal curve from a low conversion regime to a high conversion regime. Now, the focus of this talk is going to be on this discontinuity in large part, as you'll see as I walk through the data. So we compared the nickel zirconia to a nickel-free zirconia to check for sure that the nickel is the source of the activity. And indeed, this is the zirconia without nickel, showing very low activity at higher temperature. The measured CO and CO2 per mole of methane fed is shown on the left and right, and you can see that the results follow quite nicely the predicted equilibrium distribution of CO and CO2. What's kicking in at higher temperature is the reverse water-gas shift reaction, where produced hydrogen is reacting to push the CO2 back to CO. And that's why we get a maximum in the CO2 yield and an increasing CO yield with increasing temperature. Now, what's going on here? So I'm replotting now the nickel zirconia data in blue, obtained with the ohmically heated wire. I did not mention that the gap between complete conversion and nominally 90% we attribute to bypassing through the spaces in the cross-section of the tube that are closer to the wall, unreacted methane that is not seeing the catalyst, quote unquote. Now I'm comparing these data to what I would call a conventionally heated wire. And in this case, Meghana from the Bellini lab took the same length wire and snipped it up with scissors, put the pieces of wire into a tube, and carried out a more normal fixed bed reactor experiment where the heat is provided through the wall within a conventional clamshell furnace. And interestingly, you can see notable differences between what we had expected to see in the red and what we did see in the blue with the ohmic heating. At very high power, the conventional heated wire approaches complete conversion as you would expect with no bypassing. So we see the bypassing difference out here. At lower temperature, we get the conventional outperforming the ohmic heating, but interestingly, there's a range of power where the ohmically heated wire outperforms the conventionally heated wire. And that was a puzzling result at first, and that's what I'm going to try and walk you through our thinking. Okay, now Elmer, with a little bit of prodding from his advisor, after generating this ignition point, as we would like to call it, decided to change the direction of the power dialed into the reactor. And so I'm lightening out the gray circles as the data obtained when going from left to right with this ignition. And the green triangles are data obtained starting at this point and moving from right to left, dialing down the power. Now, I prodded Elmer because I have an interest in other projects over the years in what's called steady state multiplicity, where reactions and reactors exhibit multiple steady states manifested typically as hysteresis phenomena. The puzzler here is that, as we know, methane steam reforming is endothermic, and conventionally, it's only exothermic reactions that exhibit this thermal feedback effect that leads to multiple steady states. So keep that thought in your mind as I continue to walk through the data. Now, Elmer continued to slowly reduce the power and measured steady state conversion that went beyond the ignition power, nominally about 56 watts, to a much lower power, down to nominally a little bit less than 15 watts, where the reaction died. So this very interesting result kind of proved to us that not only is there a kind of ignition, but there is also a hysteresis that's obtained in the experiment. So for a pretty wide range of power, the catalyst can either exist in a very low conversion state or a much higher conversion state. What's going on? Because this is not an exothermic reaction. Multiple steady states are not supposed to happen for exothermic reactions. Now, interestingly, before I get to some mechanistic aspects, if one calculates the moles of hydrogen produced per kilowatt hour supplied, which Elmer has done, it's interesting to note that there's a kind of maximum utilization of the provided energy, electrical energy, through Joule heating that maximizes the production of hydrogen along this high branch. Too high of a power leads to diminishing returns as the conversion approaches completion. Too low of a power does not produce enough hydrogen. There's actually a sweet spot where one gets a nice balance, or a maximum in the hydrogen production or energy utilization. Now, let me show you a few more observations in Elmer's set of experiments. We decided to go and compare the zirconia catalyst support to alumina, which is actually a more conventional support for steam methane reforming catalysts. Interestingly, when we carried out similar experiments with the FeCrAl wire, now coated with a nickel alumina catalyst with the same amount within experimental error, whether we increase power or decrease power to that coated wire, we do not see any weird ignition, nor do we see multiple steady states. So a notable observation here is that the support does matter, and it is playing a role in these interesting observations that I've presented to you so far. Now, additionally, with alumina, we never see a range of temperature wherein the Joule heated wire outperforms the conventionally heated wire. The conventional heating is always more, gives a higher conversion of methane at a given temperature than the Joule heated wire when alumina is the support. Again, that is not the case with zirconia, as I showed you earlier. So let me stop here and kind of recap the data that I've shown you. First of all, the methane conversion versus applied power for nickel zirconia exhibits an abrupt ignition and steady state hysteresis of methane conversion versus power/wire temperature. On the other hand, nickel alumina shows a more conventional unique steady state. Furthermore, the Joule heating for nickel zirconia enhances the methane conversion over a range of power settings, but there's no apparent enhancement for nickel alumina. So really, what's going on here? We have multiple steady states, not expected for an endothermic reaction. We have an important effect of the catalyst support. We have no apparent activity of a wire that does not have nickel as part of the coating. And again, there's a notable difference between the catalyst support on which the nickel is impregnated. So what's going on? Well, that's going to lead us to a mechanism, and we've considered several mechanisms. This one, we believe, checks all the boxes, but it's definitely up for debate. So let me walk you through our hypothesis. We believe what's happening here is an electrocatalytic effect. In essence, conduction within the zirconia support layer serves to reduce nickel cations to nickel metal, increasing activity. Now, that statement implies the fact that it's known in the literature that reduced nickel, instead of say nickel oxide or nickel hydroxide, is more catalytically active for SMR than is the oxide or hydroxide. So we're hanging on our hat on that known fact. Now, let me walk you through what we think may be happening. So this is a schematic of the interface between the underlying FeCrAl wire and the nickel zirconia. It's obviously not to scale. So this line here is the interface. Again, the thickness of this support layer or catalyst layer is tens of microns. The FeCrAl wire, on the other hand, is about half a millimeter in diameter. So it's a thin layer. Now, under conditions of applied voltage, the electrons are obviously flowing through the FeCrAl because this is leading to an excessive heating of this resistive metal. What we believe is happening is that some of the electrons, to be quantified, are diverted through a nominally conductive zirconia layer that's supporting the crystallites of nickel catalyst. These electrons are interacting with the nickel in a reductive sense, leading to enhanced activity. Now, why do we say that? Well, zirconia is actually in the class of semiconductors. It has a conductance shown here in some data from the literature, kind of an Arrhenius plot of conductance versus 1/temperature that is activated. So increasing temperature leads to higher electrical conductivity of zirconia, unlike alumina, which is more of an insulator. So what we believe is happening is as we increase the power to the underlying FeCrAl, when we reach a certain temperature of the catalyst wire, and hence the top layer, the zirconia becomes somewhat conductive, enabling electrons to flow through it, which contacts the electrons with the nickel cations. As a result, the electrons have the opportunity to do an electroreduction of the nickel oxide / nickel hydroxide to nickel metal. And as I mentioned a few minutes ago, the nickel metal is known to be a more active support for SMR than is the cationic-based nickel. Now, this is a conjecture that we have to prove, obviously, but this looks to be an explanation for the observations I've shown you so far. So we essentially have a dynamic redox couple, we believe, in the top layer that involves directly electrical current. The reduction, which I'm reproducing here, could be represented by nickel hydroxide being reduced to nickel metal, producing hydroxide anions, which then can undergo further reaction. That is balanced by oxidation by the gas phase. We have, as you know, I said a 3-to-4 ratio of steam to methane. So we have plenty of water that can serve as a soft oxidant of the nickel, producing nickel hydroxide and hydrogen. So what we would call a dynamic redox couple is set up by these two competing reactions. Water is tending to push nickel to its less active form. The electrons are counteracting that oxidation with a reduction. Now, I should note that the stoichiometric reaction I'm showing for the oxidation liberates hydrogen. So Elmer came up with a clever experiment and asked the question, well, what is the role of hydrogen here? We do know that it's the main product from the SMR. Is it possible that the hydrogen that's being generated is pushing this reaction to the left? Well, one way of testing that is to add hydrogen. So I'm now re-showing data that I've shown you earlier. So this is for a particular 10-turn wire coil. The flow rate here is fixed at 250 cc's per minute. The green triangles are obtained on the nickel zirconia, and these are steady states that we believe exist because of the electroreduction of the nickel oxide and nickel hydroxide. Interestingly, when we add a small amount of hydrogen to the feed, nominally 2%, remembering that the feed methane concentration is 5% and steam is approaching 20%, we get the blue circles. So we basically follow the same trajectory of the conversion that we obtain in the absence of hydrogen. Now, that may not be a surprise, but what is notable is that with the addition of hydrogen, the lower steady state is completely removed. So this red lower steady state with the ignition obtained without hydrogen addition is no longer present. And so in an experiment starting at low power and proceeding to high power, we follow basically this high branch that would only exist at lower power when hydrogen is not added. But with hydrogen added, we follow this trajectory. Now, interestingly, well, from a fundamental standpoint, we have to answer this question, which we've not yet answered, is how can we actually predict the existence of multiple steady states for an endothermic reaction? And what I'm suggesting here is that something that we still need to do, but we believe that we're getting catalytic enhancement due to the flow of electrons through the catalytic layer, which is serving to affect the activity of the nickel catalyst. And one way of testing that would be to semi-empirically make either the activation energy or the pre-exponential factor a function of the conductance, which itself is a function of temperature, and to put that into the energy and material balances and see if the resulting mathematical model exhibits or predicts multiple steady states. We've not done that yet, but we will be attempting that in the coming weeks. Now, I want to finish off the last few minutes just showing that we're not stopping with experiments. We're doing some simulations. Elmer is applying COMSOL with good old reaction engineering analysis to analyze different variants on the reactor that we envision could result from this electrically heated wire experiment that was confined to one wire. Now, now you'll have to kind of humor me, but I'm showing the experiment on the left with the coil and arguing that in a two-dimensional envisioned reactor, looking at it from the side, we would have a set of rods or wires that are parallel to one another and staggered in two layers here. And our approach in the synthesis of possible reactor types is to cascade many layers of wires along the length of the reactor tube to simulate a multi-wire or multi-rod reactor. So the approach that we take is to take known kinetics of SMR from the literature. This is from the Guy Marin group in Belgium, from AICG Journal. We take those kinetics, put them into the material balances appropriately. We have energy balance. We have a diffusion and reaction within the catalytic layer. And then COMSOL allows us to simulate the local environment of the coated wire, wires, I should say. Now, our envisioned reactor is shown here schematically. So we have flow from left to right. These are all rods in this case. Here's our inlet conditions, and I'm just showing you some results of some simulations with these conditions in mind. So a 30% methane, 70% steam with these conditions coming in, preheated, atmospheric pressure, fully developed flow, and here's the volumetric flow rate. This is a two-dimensional reactor where the catalyst rods are coming out at us from the screen here. So these are 170 Canthal rods that are half an inch in diameter and coated with nominally 20 microns or so of nickel supported catalyst. We put all that into the reactor and simulate away, and I'll show you some results. This is the methane profile in this 100+ rod reactor where we are supplying nominally 100 amps of current per rod, given a total power input of 6 kilowatts. That's converting about 45% of the methane, and this shading shows the consumption of methane from left to right. You can see the little plumes around each wire showing the gradients of methane in the vicinity of where the reaction is happening. So the reaction only happens, and that's an assumption, on the catalytic layer. The corresponding hydrogen profile is here. We can quantify the amount of hydrogen generated per mole of methane consumed. It's about 3.5 moles, so somewhat over 3, with the forward water gas shift participating in the generation of additional hydrogen beyond the 3 for SMR. We can also calculate a hydrogen production per power kilowatt hour of nominally 0.68 normal cubic meters of hydrogen per kilowatt hour. Here's a temperature profile. You can see, and this is to be expected, we have the heating from 200 degrees to a much higher temperature. The highest temperature we see in this particular simulation is 1360 centigrade. The minimum wire temperature is 427 degrees centigrade. So there's heating from left to right. Reaction is occurring along the length. Now here's the hydrogen productivity versus input power for 3 different flow rates. And as you would expect, the more methane that we put in, as long as we provide enough power, the more hydrogen we produce. And it kind of peters out because of equilibrium limitations that I've described. Now, what happens if we increase the number of rods from 170 to about 700? So this is a kind of experiment on the computer where we look at a more densely packed tube with now 700 rods to increase the productivity of the same volume of reactor. Here's the results comparing about a factor of 3 or 4 more rods, going from a conversion of a little over 30% at this flow rate for the 170 rods to a conversion approaching 80% at a power setting of about 13 or 14 kilowatts. Now, I'm showing you a discontinuity here because we cut off the simulation because the wire is getting too hot, and that would lead to a melting of the wire. So that's a self-imposed constraint on these computer experiments. Now, it's interesting to calculate the electrical productivity of the production of hydrogen for the two different densities of rods. And for the 700 rods, we're approaching about 1 cubic meter of hydrogen per kilowatt hour. It's interesting to compare that to state-of-the-art electrolysis, which is on the order more of about 0.2 cubic meters per kilowatt hour. And that's not a surprising result, but it's basically reaffirming that thermodynamically, it makes more sense to make hydrogen from methane than it does to make hydrogen from water. But it does suggest that from a scale-up standpoint that we can meet some interesting productivity levels with this kind of concept. So those are just a few of the simulations. Let me stop and say, leave you with a question. Is this the future of steam methane reforming, catalytic cracking, and other important endothermic reactions? That remains to be seen, but I think the results are encouraging, at least for SMR. We found a unexpected consequence of the imposed ohmic heating on the catalytic activity, and hope to have more insight into what we believe is happening as we move forward. Now, without the support of Shell, this research could not have happened. The project supported a collaboration between myself, Bala, and Praveen, together with our Shell collaborator, Ram Ratnakar. The 3 students who have been working on the project include Elmer, Meghana, who prepares catalysts and does kinetic studies, and Collins, who's doing some additional modeling of this reactor concept. With that, I'm happy to answer any questions that are out there in the audience. Thanks for your attention.